Algebra 2 Honors 3.6. And on this one, you're going to be solving quadratic inequalities, and there'll be graphing, and there will also be using an algebraic process to solve these. And when you have inequalities instead of equations, you get these infinite solution sets where we have to shade the graph to see, we get a visual of these solutions. We can't really name them all. So it's kind of interesting. And so what we're going to do is you are going to notice that it's an inequality, because that's important in terms of just knowing that there's a little different process. So note that it's an inequality. That means then we're going to follow this process over here of step 1. Graph and use dashed for inequalities with less or greater than. So this is a greater than, so we use dashed, or use solid for inequalities that contain equality. And that's part of the points for this, so you need to do that appropriately. And so now we have this, we're going to treat it as y equals negative x squared minus 2x plus 15. It's in standard form. So let's look at that axis of symmetry by using a negative b over 2a, which is going to be 2 over 2 times a negative 1, which is negative 1. And then plug that in to find the y value. So f of negative 1, negative 1 squared minus 2 times negative 1 plus 15. And you get negative 1 plus 2 plus 15. And so that is going to be 16. So the vertex of this is negative 1 comma 16. And so I prepared for that, and I scaled the y-axis going up by 2's. So we've got negative 1 and 4, 8, 10, 12, 14, 16. So there is my vertex. It's opening down because A is a negative 1, but it's the normal opening. And so if I go the right one, I go down, oops, down 1's going to be right in the middle because this is going by 2's. If I go the right 2, I'm down 4. And it just so happens that this, if I take out a negative, this factors. And so I have intercepts at 3 and at negative 5. So that can help me. And if I put in a value of 4 into this, just trying to complete the graph and get all the points in there. I get negative 9. And so at 4, if I go to 2, 4, 6, 8, 9, and that would be reflected over here. So I'm just getting a bunch of points, but now you have to make sure you dot this, because we're not including points on the parabola, because this is, I just want values of y that are greater than the right-hand side. And so what we do at this point is we're going to be shading. We're either going to shade inside the parabola or on the outside. And they say test a point on the inside. I say do a test point that's easy to choose. So if I do the, and so what we're going to do is we're going to test a point. So I'm going to just test the point 0, 2. It has to be not on the parabola. They suggest picking a point on the inside. So 0, 2 would be right here. And then we're going to plug it into that original inequality. And so the y value of 2 when x is 0, it's kind of nice to use an x value of 0 here because things calculate out so nicely. Is 2 greater than 15? That is a false statement. That means that this point is not a solution. And so when it's not, then we are going to shade on the other part of the graph. We're going to shade outside the parabola. Since a point inside, when put into the original inequality, did not satisfy the equation, we shade on the outside. If that point would have satisfied it, we would have shaded on the inside. And so what that means, if I pick a point out here, oops, I didn't want to do that. If I pick a point, out here and out here, all these points, any point in here, if I use the ordered pair and plug it into the inequality, y will come out greater than the expression on the right. Those are all the points that satisfy it. There's an infinite number of them. There's lots and lots and lots of them. So how we express the solution set is via a visual graph. Okay, so then an application of this is this example 2, the allowable bending load, M in pounds, of a certain size concrete beam can be expressed as M is less than or equal to 540 d squared. So if you want to kind of think of that as y is equal to less than or equal to 540 x squared, this is quadratic because the x is being squared. It's an inequality because it's not an equation, it's not equal. So this has to do with, then if I do this graphically, I'm going to think about shading an entire region. And so anyways, graph the inequality and interpret the solution. So I need to graph this. And so I'm going to do a table of values. That's got a vertical stretch of 540, but if I put in 0 for x, y is going to be 0. So it starts at 0, 0. So if you don't have any diameter on the concrete beam, then it won't have any pounds. Matter of fact, I would say that's really not part of the domain. That's probably an open hole because it doesn't make sense. If you don't have a diameter, you don't have a beam, or a concrete beam. So anyway, so that's kind of the startup. And so, by the way, while we're talking about that, let's talk about domain. The diameter has to be positive, and the bending load has to be positive. So we are really only talking about the first quadrant. So we're not going to worry about, y equals 540 x squared would, have something that looks like this, I guess a lot narrower, but we can't, in this application, use where x is negative. We can't have a negative diameter. So domain is part of this problem in figuring out your solutions. So anyway, so if I do that, and then I'm just going to kind of make it easy on myself. If I let the diameter be 1, 2, 3, and plug it in, well, if it's 1 squared is 1 times 540. If I put in 2, I get 540 times 2 squared, so 4 times 540 is 2160. And then if I take 540 times 3 squared, so 9 times 540, and notice that I had pre-scaled the y-axis going up to 4,000, so we're already going, hitting the top of our graph here. Of course, you have to kind of scale your graph after you make the t-table in order to be able to fit the points. And so now we're just going to go ahead and plot these. If I go to the right one, I'm up 540, which is just slightly above there. If I go to the right two, I'm at 2160, slightly above there. And then at 3, I'm at 4860, almost up to the 5,000. And then I'm going to go back. Do I dot or do I make it solid? But it said when you have less than or equal to or greater than or equal to, you make the line solid. So I'm going to do that. So come here and just, it's a parabola opening up, vertex at the origin, and it just keeps on going. Now, I need to decide if I'm shading inside the parabola or outside the parabola. And so I'm going to do a test point. And what if I tested this point 0, 1000? And if I plug that in, is 1000 less than or equal to 0? Well, that is a false statement. So I'm not going to be shading inside. I am going to be shading outside, but only in the first quadrant, because it doesn't make sense to have bending weight negative. And so we're just going to keep it above the x-axis, or in this case, the d-axis, and indicate those are my solutions. But we're not done yet, because it says interpret the solution. And so this shaded region are the allowed diameter and bending loads for the concrete beam. So shaded region gives the allowed diameters of the concrete beam in inches with their corresponding loads, right? Bending loads. And those are in pounds. So there you've got that. All right, so so you need to, reread the problem, make sure that you have answered everything. So this takes a written sentence to interpret the solution. All right, so example 3. Graph a system. Well, when basically you're going to do what we did in example 1, graph both parabolas, and then you're going to find where you have points that satisfy both of these. So it's basically two problems kind of combined together, and then there's a final heavily shaded region so that you know where the solution set is. So treat both of them just like we did in example 1. First of all, we're thinking y equals x squared minus 4. That is the basic parabola shifted down 4 units. And since being the inequality does not contain equality, it's just greater than, we're going to dot this. And it's a parabola at -4. Normal opening, right 1, up 1, left up 1, right 2, up 4, left 2, up 4, right 3, up 9. Use symmetry and fill out the graph there, get accurate points. You need to have several accurately plotted points, and it's dotted. Excuse me. And so then I'm going to do a test point. And since 0, 0 is inside it, that's just a nice point to test. So if I put 0 in, I have 0 greater than -4. That is true. And so 0, 0 is right here. That makes it true. So now your end answer has to be the overlapping shaded regions. So in this case, just very lightly, sometimes I like to put, I'm going to do different diagonal directions with the lines. I'll show you that when we get to the second one, because this isn't the final answer. I've got to have the intersection of the two shaded regions. So then go to the second equation, and I'm going to get the axis of symmetry by using a negative b over 2 times a, and plug that in to get the y-coordinate. And so I'm going to have a negative 9/4 plus 9/2, which is going to be 18/4, plus 4, which is 16/4. Just anticipating that I need a common denominator. And so that comes out to 25/4, which is 6 1/4. So my vertex is at this 3/2, comma 25/4, which is 1.5, comma 6.25 in terms of thinking about where I'm going to go graph this. But this opens down. It has an a value of -1. So I'm going to go to the right 1.5. Might as well pick up, I should just pick up a different color here. So go to the right 1.5 and up 6.25. So in here, I'm going to get that darker. And then if I go the right one, I go down 1, left 1, I go down 1. The y-intercept on this is 4, so I know if I put 4 there, then I'm going to be at 4 here. And if I go to the right 3, I would go down 9. We're up at 6. So about right here. And there I've got, now this one is solid because you have equal to. So I've gotten some accurate points in there and plotted, but now I have to pick a point to test on it. And I want to make sure that I am not choosing something that this parabola is on. So I could pick maybe, say, the point 1, 2 and plug it in. And so if I plug in 1, 2, 2 is less than 6 is true. And so I'm going to have the diagonals on this just go the other direction. And then you have to sit back and go, where is it that both of these are shaded? That is your solution set. And where both of these are shaded are in here. So you need to go and make this part dark, shade it heavily so you know that is your final answer. So I want to kind of go in here and shade this heavier and make it very clear that that intersection is my final answer. So that's graphing a system of inequalities. So being able to graph a parabola and being quick at it and precise is important. So example 4. Now this is huge. You need to, when I give you the you try it, you really need to stop the video and you try it, because solving this inequality algebraically, I want the x values that will make this positive. This is the process that you need to use. And so what you're going to do is you are going to factor this. And we have an x plus 8. and an x minus 4, and don't forget the greater than 0 as you work down. And so the thing is that you need products of numbers that are positive. Well, there's going to be a lot of values of x that probably will make this positive. So there is a process. And the idea is the zeros of these are -8 and 4. And at -8, if I put -8, it's 0. If I put 4 in, this expression is 0. Since polynomials, quadratics are smooth curves, the only chance it can change from positive to negative is when it goes through zeros. So those zeros of -8 and 4 are super important because they're the only possible places where this can change. So we call those zeros my key numbers. This is an important process to understand. So we factor it. We find the key numbers, which would be the zeros from our factored form. Again, it has to be compared to 0. And then we're going to make a number line. So I want to see the number line and just plot a -8 and a 4, label those, because what at -8, this inequality is 0. At 4, this inequality is 0. And what this does is it breaks up my x values into intervals. And I'm going to make a table of values. And so we have from -infinity to -8. And then we have -8 to 4. And then we have 4 to positive infinity. And so what I need to do is pick a test number inside each of these. So I would use an x value of -9. So I'm going to label that and make this chart just like this. So you have your test number. So I'm going to use -9. Between -8 and 4, if 0 is in the interval, I like to use 0 for my test number. And then to write a 4, I'm just going to choose 5 because this I don't want to get it to be too large. And then basically what you're going to do is write that factored form here. And we don't have to evaluate it. We just need to think, if I put a -9 into x plus 8, that first quantity is negative. A -9 plus 8 is a -1. I just need to know that's negative. If I put -9 into the second quantity, -9 minus 4 is negative. It's a -13. But because you'd end up multiplying that, that overall is positive. And so that means the y values are positive in the interval from -infinity to -8. If I plug in my test of 0, 0 plus 8 is positive. And yes, I want the chart done just like this with the positives and the negatives. Everything I'm showing you is what I want on these. If I put 0 in for x, or 0 minus 4, you get a negative, and a positive times negative is negative. And then if I plug in 5, I get a positive, and 5 minus 4 is also positive, so this ends up being positive. And so in the interval from -8 to -8 to 4, the y values are negative. In the interval from 4 to infinity, the output would be positive. And I want values of x that make this expression positive. And so my solution, and you need to come out and state that solution, is our interval values of x. So it is -infinity to -8 because that made the expression positive, all those x values inside there. And then union 4 to infinity. So you try this. I stopped the video and you try and solve this next one algebraically and see if you come up with the right answers. Okay, let's see how you did. So this factors x plus 4, x minus 3. And so my key numbers are -4 and 3. So on my number line, those two values make this 0. And then I'm going to have some test numbers. So I would use x is -5 in this interval, I would use x is 0 in this interval, and I would use x is 4 in this interval, and then need to show those intervals. So those x value from -infinity to -4, and between -4 and 3. So it is the zeros that you are using to break up your intervals, your x-intercepts, and which is something we did before where we were determining where functions were positive and negative. We used the x-intercept, the x-coordinates for that. And then it's from 3 to infinity. Those are my intervals. And then my test numbers. And by the way, you don't have to write the test numbers on the number line, but you do need them in the chart. And then show what you are putting those test numbers in to, which is the factored form. And then show if I put -5, I get a negative. Put -5, I get a negative. And negative times negative is positive. If I put 0, I get positive, and then I get a negative. Negative. And if I put 4 in, they both happen to be positive. Positive, negative, positive. So this is the work that you need to show. And now there's a little something different on this one. Well, a couple of things. I want the intervals that make the x values that make this negative. So I'm going to be choosing -4 to 3, but I also want the values that make it 0, and -4 and 3 are zeros. So in this one, you need to include the -4 and the 3 in brackets. I don't like that. And that is your solution set. So that was a little bit of a trick there. So if you got open parentheses on -4 to 3, you did a good job. This is a new learning. So now you need to know if you include the equals 0, that you have to include the x-intercepts. All right, so this next one, graph this, and you need a calculator. And so to graph this, I'm going to go ahead and use x is a -b over 2a. I'm getting a -1, and I'm going to plug that in to get the y-coordinate of the vertex. So I get 2 minus 4 minus 3, which is a -5. So the vertex of this is -1, -5. And so if I go to the left, 1 and down 5. This is a parabola opening up, y equals 2x squared, and it has a vertical stretch of 2. So if I go to the right one, I go up 2. Left one, I go up 2. If I go to the right 2, I normally go up 4, but I have to double that, so it's going to be up 8. And then reflect that. And then if I went to the right 3, it would be up 18. So it's going to come off. And I'm going to make it solid because that contains equality. And the solutions to this, much like what we were doing in example 4, have to be a range of x values. We need to use interval notation. And it is the x values that make this expression negative or 0. So that just means for what x values is this graph below the x-axis? And it is this set of x values right here. So if I can figure out this x-intercept and this x-intercept, it's the x values in between those that are going to be the solution, including those because we have equality. Well, guess what? These weren't nice x-intercepts. So we need to figure out what those values are, but we have ways of finding what x values make this 0 when they aren't nice, neat integers. And it's the quadratic formula. So I'm going to use the quadratic formula. And plug this in. And I notice the x equals, notice the 0 equals 2x squared plus 4x minus 3, because that's what I'm trying to find, are those boundaries, those x-intercepts. And I said calculator needed. And since we are going to just approximate those two x values, so we're going to split it up. It's a -4 plus root 40, you don't have to simplify that, just because you're going to get the approximation anyways, and that's about 0.58 to 2 decimals, or x is a minus 4 minus the square root of 40 all over 4, and so that is approximately a negative 2.58. And so that means this x-intercept must be negative 2.58, comma 0 approximately, and this one is 0.58, comma 0. So it agrees with where, visually, graphically, that they were in there. So those are the two x-intercepts. And it's the values in between those that for which the graph is negative, which is what I'm solving for because we want less than or equal to 0. And so my solution set, now it contained equalities, so we are going to use brackets. So it's all x values in between negative 2.58 and 0.58. And there is my solution set. Right. And then example 6, a rectangular playground must have a perimeter of 320 meters and an area of at least, so that at least right there is where we get our inequality, at least 5,000 square meters. Describe the possible lengths of the playground. You will need a calculator, round to 2 decimal places where needed. So write equation inequalities for perimeter and area, because so we've got, should have a little diagram. We've got length and width, and we know 2L plus 2W. We know that the perimeter is 320 meters. And the area formula, that area has to be greater than at least. So at least includes it, greater than or equal to 5,000. So your length times your width has to be greater than or equal to 5,000. Like that. So area, there's that. And what you're going to do is solve either for L or W and substitute to get the inequality in terms of one variable. But it says use these to write an inequality in terms of length. So I need to get it in terms of L. That means I'm going to replace W, so I need to isolate W and replace. So I want to replace W, so that's what I need to solve for. So solving for W, and then I'm going to substitute that in for W here, and then I will have an inequality in terms of length. So that is length times 160 minus L greater than or equal to 5,000. Now, you can't solve these without getting them compared to 0. So you need to think through this. We have 160L minus L squared greater than or equal to 5,000. And then I kind of prefer that L squared is positive, so I'm going to have the left side be 0 and move that L squared over. And there is my quadratic. And so if I write that quadratic on the left, now the quadratic is less than or equal to 0, so since I switched sides, I have to flip the inequality. So there I've got something that now relates to what we've been solving. It just doesn't have x squared and x in it, it's L squared and L. But that is something that I expect that you can do. This is a traditional problem where you're given a fixed perimeter and we're trying to maximize area or get area to be something. And that process of isolating a variable, substituting, and getting the equation, quadratic equation, is just a traditional math problem that you should be solid on. Now, I don't want to sit and try and factor this. And also it said a calculator is needed, so I'm thinking, I need to find the value of L and it's not going to be a single value or two values. It's going to be a range of values. We're going to write our answer in interval notation. Values of L that will make this expression negative. So it's similar to the process that we just did in example 5. We're going to go ahead and use the quadratic formula to find where is this 0. So where is this expression 0? And those would be, if we graphed it, the x-intercepts of it. We weren't asked to graph this, but where this is 0 is going to be L is equal to a negative b plus or minus the square root of b squared and 160, so well, 16 squared is 256, and you'll have a 0 from each of that, so it's 25,600, minus 4 times a times c, all over 2a. And don't try to reduce the 2 and the 160, you can't, because you don't have a number in front of the radical that is divisible by 2. And so that's 5,000 times 4 is 20,000. So if I subtract, I get, you don't have to do too much simplifying because you're going to use a calculator anyway. And so that means L is 160 plus the square root of 5,600 over 2, and this is where you pick up your calculator and evaluate, which is about 42.58 2 decimal places, or L is 160 minus the square root of 5,600 over 2, which is approximately, so the approximately equal to sign. I think I did that opposite. This subtraction is the 42.58. And the addition, I was just copying values, sorry, 117.42. So those are my key numbers. So if I had, a number line, I'd have the 42.58, and then I would have the 117.42, and those make the area, that expression 0. And so I want it to be at least. And in this one, you could do test numbers in each category. Since I'm looking at this expression right here, I know it's a parabola that's going to open up. Now, you have to have tables of values on these where I'm saying algebraically no calculator. You have to have tables of values on those. On this one, I'll let you go ahead, and there's enough going on here. It's a parabola opening up, so I expect that these are the zeros. It's up, opening up, so it's going to go positive, negative, positive. And so what is my overall answer? And I need for the area to be greater than or equal to 5,000, and it said values of L that make this negative. So between 42.58 and 117.42 makes this inequality, that left side negative, which are my solutions. And it said or equal to 0. So my solution says the solution is that you need lengths between 42.58 meters and 117.42 meters inclusive. And the inclusive means that we're going to include 42.58 and 117.42. There you have it.